So, welcome student to the next class of Introduction to Nonlinear Optics and its applications. In the previous class we discussed about the Carr effect, and then we started something related to the symmetry in susceptibility, third order susceptibility. So, today we have lecture number 43 and let us see what we have in today's lecture. We have the symmetry in third order susceptibility and then study the cell phase modulation. So, symmetry in the third order susceptibility, we started this very quickly. We mentioned in the last class that if I want to find out the degeneracy factor, because when the nonlinear polarization is written, it is in the component form, it is written as ith component of nonlinear polarization. If I write in nonlinear here, is epsilon 0 chi I j k l, and then E j E k and E l. Now, when I write E j E k E l and I j k here, these are the repetitive indices. So, we know that this repetitive indices means there should be a summation sign over here. So, we should have a summation sign over j, k and l. Now, the question is, if we have this kind of formation that if this has a frequency component omega 1, omega 2 and omega 3, and then if these three things are multiplied together, these things j, k and l are distinguished, then what happened? Then we will have a frequency component omega 1 plus omega 2 plus omega 3, and with this we write this frequency component as omega 4. So, that means P nonlinear here omega 4 will be the multiplication of these terms E j, E k, E l, both having frequency component 1, 2 and 3. Now, if any of these two are same or three of them are same or none of these things are same, there should be three different conditions, and for three different conditions what we have a degeneracy factor. So, one factor will appear here, and this degeneracy will come, this degeneracy factor will come because these things may same. If they are same, then we will have one distinct field and we have d equal to 1. So, this is 1. If two of them are same and one is different, then we have a value 3 here, and if none of them are same, so 3 are totally distinct field, then we will have a degeneracy factor 6 here. So, this term will appear several times when we do the calculation, and why they are coming we can understand very easily, because this term, if I write my total polarization in scalar form, the nonlinear polarization rather in the scalar form, which is very effective as I mentioned several times, it should be E total whole cube. Now, if E total contain two different fields, say E1 and E2, so this cube is nothing but the cube of this. So, eventually we have A plus B whole cube. So, when we have A plus B whole cube, so we will have one term like E1 cube, one term like E2 cube, and the combination of these two like 3 E1 square E2 and 3 E2 square E3. Since we have only two distinct field, we have a number 3 here and a number 1 here as a degeneracy factor, because if I expand, it should be E1 cube, which has a degeneracy factor 1, plus E2 cube, which has a degeneracy factor 1 here, and then we have E1 square E2, two fields are involved, among which we have two identical fields. So, that means it follows this. So, we have 3 term here, and another case we have 3 E2 square E1. This is also possible, and here also we need to write 3 because two distinct field and one field is different. So, in order to understand these things, let us put some kind of example. The same example I showed, I show. So, here this is the case. So, total electric field is this E plus E2, where the frequency component omega 1 and omega 2 are there. So, two different frequency component. So, P NL is nothing but ET whole cube. ET is this plus this. So, I need to make a cube of that. So, when I make a cube of that, what should be the frequency component, that is important. So, in first case we have E cube of omega 1. So, when we have E cube of omega 1, the frequency component is written here, we have 3 omega 1 frequency. E3 of omega 2, we have what frequency component? We have 3 omega 2 frequency component. So, total frequency component here is 3 omega 2. 3 of E2 omega 1 and then E omega 2. So, what will be the frequency component? The frequency component will be 2 omega 1 plus omega 2, and in the similar way here the frequency component will be omega 1 plus 2 omega 2. Now, if I want to find out my frequency component, this is a specific structure, and for this specific structure we have 3 fields sitting here, and from these 3 fields I now want to find out my nonlinear polarization with a particular frequency. You can see there are different frequency that can appear in P nonlinear. So, P nonlinear can contain 3 omega frequency, it can contain 3 omega 2 frequency, it can contain 2 omega 1 omega 2 frequency component and omega 1 2 omega 2 frequency component for this particular structure. So, there are 4 different frequency components are there which can appear in P nonlinear, but we now only need to find out the frequency component 3 omega 1. So, how we can find 3 omega 1 frequency? By adding omega 1 and omega 1. So, when I add 3 omega 1 together, then only I can have 3 omega 1 frequency. So, this we can only have when we have multiplication of these first 3 things, and once we have a multiplication of these first 3 things. So, these 3 fields have to be the same field because they have the same frequency components, and we have a degeneracy factor here, and this degeneracy factor have to have value 1 because they are all same. What should be the frequency component of 3 omega 2? So, 3 omega 2 frequency component one can have for this particular case by omega 2 plus omega 2 plus omega 2. Again the degeneracy factor has to be 1 here because all these frequency components should be same. What should be the frequency component of 2 omega 1 plus omega 2? This is the frequency component that should have in P nonlinear. In that case, what happened? I need to add 2 same frequency omega 1 omega 2 and 1 different frequency component, that means other field will be multiplied, and that is why we will have a term 3 here. In the similar way, we have a degeneracy factor 3 here because again we have 2 omega and 1 omega 1. So, 2 distinct field and 1 different field, that means a degeneracy factor 3 will be multiplied here if I want to calculate the nonlinear polarization of frequency omega 4. So, in this way we will calculate this. So, please remember this because we will going to use this in the previous in some future classes. So, now some other permutation symmetry of chi3. So, permutation symmetry we have already seen when we calculate the second order susceptibility. Because of the Newman symmetry and other symmetries, we find there are many components that will going to be vanished, and there are many components which are equal to each other, and eventually we find that there are few components which are distinguished, other components are same. Here in this case also we will have a similar thing. So, here we have a comparison. So, total number of component of chi2 is 3 to the power 3, which is 27, that we know. So, there should be 27 different components, but we find that among these 27 not all are different, there are many same components are there. So, we can reduce the total matrix. Here also for chi3 we have 81 different components, but it should have a permutation symmetry. So, because of this permutation symmetry, what happened that susceptibility IJKL should be equal to susceptibility JIKL, KJ, KLJI and so on. And also for a specific isotropic system, this susceptibility terms, these different terms, the 81 different terms can be reduced to only 21 different terms, because they have some internal symmetry here. So, this internal symmetry suggests that XX, YY and ZZ, they are same. If all these components are same, then they are equal, and these things will be again equal to XX, YY, XY and XYYX. There can be 4 different types of this. So, one type is 2 components XX and YY are sitting side by side, like YYZZ and ZZXX, and then again XX, YY, XX, ZZ, YY and XX, ZZ. So, all these components are same. Again there are some components XY, XY, YZ, YZ, these are again of type 2, they are same. Finally, we have a mirror kind of things. So, XY, YX, YZ, ZY, these components are again same to each other. So, now if I try to find out, so these are 21 different elements that one can reduce for isotropic system, other components are not there. So, how these 21 components are there, you can see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. So, these 21 components are there, but they are also related to each other. So, eventually we will have only 3, this and this and this, these 4 different, and again we have one equation to in our hand, so that we can have only 3 components that are different. So, among 81 components we have only 3 components that are different. So, this kind of symmetry can be possible in chi3. So, you just remember that it looks that it should have 81 different components, but the thing is that because of the application of the symmetry or the material symmetry, we can reduce this radically and eventually have 1 to 2 components which are non-vanishing or they are distinguished. Well, after having this knowledge of susceptibility, symmetry of the susceptibility, let us again go back to our original problem, that is, if I launch an electric field omega, then in the system 2 frequency components will generate 3 omega and omega, and if it is generated, then the total electric field inside the material is now represented in terms of omega 1 and minus omega 1 and 3 omega and minus 3 omega, like this. So, it is omega minus omega, 3 omega minus omega, the complex conjugates are added here. So, eventually we have 4 different frequency component. We can consider these complex conjugate components are also different frequencies. So, there are 4 different frequency component, omega, minus omega, 3 omega and minus 3 omega. So, inside the system let us consider 4 different frequency components, and now they are combined with themselves and find different frequency component of PNL. So, the challenge here is to find out the different PNL value with different frequency component. So, now the PNL can be represented as susceptibility epsilon 0 into third order susceptibility multiplied by E1, E1 star, E3, E3 star. E1 have frequency component omega, it has frequency component minus omega, it is 3 omega and it is minus 3 omega and cube of that thing. Once we have cube of that thing, eventually what we are doing, we are solving the problem A plus B plus C plus D whole cube of that. So, how many terms will be there, you can imagine. So, these amount of terms are there. So, this amount of different frequency component will be there. A cube, B cube, C cube, D cube will be there. So, one frequency component will be 3 omega, another frequency component will be minus 3 omega, another frequency component will be 9 omega and then minus 9 omega and so on. There will be other term also. If you calculate this A plus B plus C plus D whole cube, you will have A cube plus B cube plus C cube plus D cube plus 3 of A square B plus 3 of A square C plus 3 of A square D plus 3 of B square A, 3 of B square C, 3 of C square D and so on. So, all the combinations will be there, and also one combination will be there, and that is 6 of A B C D, something like this, 6 of A B C and then plus 6 of A B D plus 6 of B C D. This kind of components are there. So, A B C is the 3 different components, so that is why 6 are there. A B D are different components, that is why 6 are there. So, for all different components we have 6 degeneracy term are there, which we have already discussed in the previous slide. So, as I mentioned, there are different components will be there, but our goal is to find out only few components, and these few components are omega, how the omega components are there, and 3 omega components. So, if I make a cube of this quantity, so how we can get the omega components? So, omega components, the first way to get the omega component is E omega multiplied by the E omega star. So, there will be omega 1 omega minus omega, so 0, and then multiplied by E1 omega. So, one term will be here, so that we have omega component. Also we have E3 star, which gives you 0 omega component, and then multiplied by E1 omega we will have the omega component. What we need to do, that whatever is written here in the bracket, you just add and check whether you are having a omega or not. So, if you have omega, then these are the omega components. So, that means the total contribution of these terms is omega. So, this term will have a frequency component omega. Again, one can have omega by E1 star, which is minus of 2 omega multiplied by E3 with 3 omega. So, if you add minus of 2 omega, which is minus of omega, it is minus of 2 omega plus 3 omega, again you will have omega. Interesting thing is this, again the degeneracy factor. You can see we have to have a degeneracy factor 3 here, because E1 star is different, but E1 is same. So, how many distinct fields are there? Only 2 distinct fields are there, E1 star and E1. By the way, here E1 star and E1 should be considered 2 distinct fields. Here we have how many distinct fields? E3 star and E1, 3 distinct fields are there. Since 3 distinct fields combine to generate omega, we will have a degeneracy factor 6 here, because according to our rule, if 3 fields are different, so we will have a degeneracy factor 6. Here again E1 are same, E1 star same, E3 is different, so we will have a degeneracy factor 3. So, now if I recollect all this term, we will have few terms here, and this is this. The first term is mod of E1 square E1 with a 3 multiplication and e to the power of I k1z, because k1z will be the phase term. This term is related to cell phase modulation, because we know that E1 is half of e to the power E1 omega is half of E1 e to the power of I kz minus omega t minus omega t. So, if I use this E1 here, then what happened, this exponential term will have, we will have this exponential term and this amplitude term, and we write this in this way. So, if I write this in this way, so exponential term will come here. So, entire term will have a frequency component omega. So, e to the power I omega t will appear all the time. So, I can take it as common, and then we will have this term which is related to cell phase modulation, this term which is related to the cross phase modulation, and finally, other term which is related to the third harmonic generation term we will discuss later. Well, in the similar way, if you try to find out what are the 3 omega components, then I can give this as a simple homework for you. Then you will find that there are terms which you will gather is E1 cube, which is the third harmonic generation term, and cross phase modulation term and cell phase modulation term. What is cross phase modulation? What is cell phase modulation? Let us try to understand very briefly. Here we have a cell phase modulation because all the terms are related to E3. Here we have a cross phase modulation term because one term is related to mod of E1 square and another term is E3. E3 is a natural term because we are talking about 3 omega frequency. Here also we have a cross phase modulation because E3 cube is there and natural frequency term E1 is sitting over here, and also E1 mod of E1 and E1 is sitting here. So, this is the same term. So, that is why it is called the cell phase modulation and cross phase modulation. In cell phase modulation, what happened? The pulse phase will modulated by its own, and for cross phase modulation, that means the pulse will get modulated, the phase of a pulse is get modulated by other field, and here the other field is the E3 field. That is why it is called the cross phase modulation. Well, once we have all this term, now it is time to find out the equation for cell phase modulation, and in order to find out the equation for cell phase modulation, we just need to solve the nonlinear Maxwell's equation that we have been solving for last few classes. So, this is the standard form of Maxwell's Maxwell's equation. We don't need to explain this every time, because I believe by the time you are very much aware of this equation, because this is the mother equation, and from that we need to derive the evolution of the fields, the field amplitude rather. Total electric field is this. So, once we have the total electric field form, now it is time to have this value and this value related to E1. So, if I do, the grad square of E1 is simply this quantity, double derivative of E, single derivative of E, and the derivative of the exponential term, which gives me E1 k1 square with e to the power I kz minus omega t phase sitting over here. Now, we use the slowly varying approximation, which suggests that this term will going to vary very fast compared to this. So, we can neglect this term, and if I neglect, my equation will now confined with these terms. Also, we have the derivative of E1. So, once we have the derivative of E1, so if I do these things, so here in the equation I just miss E1. So, you should put it E1, okay, here it is written E2, it should be E1, and here it is typing mistake. So, here should be E1. Anyway, so if I do this derivative with respect to this t, then what happened, that we will have minus omega square term outside. So, minus omega square term outside, and rest of the term will be simply E1 e to the power I k1z minus omega t. So, we can evaluate this thing quite easily because we have been doing that for our last few classes. But the interesting thing is the source term. The interesting thing is this source term. This is the source term. If you remember, you will find that this source term is containing many things here. So, if I consider P n l omega, then we find that it is containing many terms here. So, we need to take care of these issues. So, now we will have a source term containing the cell phase modulation, cross phase modulation term, but we are now only looking for the cell phase modulation effect. So, I am only taking the cell phase modulation as a source term. So, that means only consider this term. We are now not considering this effect for the time being. We will do that in the later cases. So, if I consider this as a source term, the derivative of this quantity simply will be 3 by 8 epsilon 0 chi 3 and then minus of omega square mod of E1 square E1 and this quantity. Now, if I plug these things to our original equation, this equation will be simply this. So, we know that this term and this term will cancel out eventually, because k, we know that this is always these two terms are always there and they will going to cancel out each other, and now the source term is slightly different. One interesting thing here is to note that this is a naturally phase matching thing. So, in the right hand side we have e to the power I k1z minus omega t, in the right hand side also we have e to the power I k1z omega t. So, this phase thing will not be there. So, it is a naturally phase match term. So, cell phase modulation will naturally happen whether it is a phase matching or not. So, we have this term in our hand, again this thing and this thing as I mentioned cancel out, because k1 if we calculate it will be omega square mu 0 epsilon, and k1 this term is omega square mu 0 epsilon. This negative term will be positive and this term will cancel out, and right hand term will be as usual. So, then we will have 2 I k and these things in the right hand side, and then if I put this 2 k I in the denominator and just put the value of k1 is omega by c into n1 here. I put n0, it should be n1 because I am my notation it is now n1 anyway. So, it will be simply this quantity. So, this is the equation for cell phase modulation SPM. So, this equation suggests that a field amplitude E1 will evolve, and in the right hand side all the term are E1. So, that means the field will going to evolve and this evolution will not depends on any other field. So, E1 will evolve by itself. If I want to write these things, in terms of intensity, we can always write this. So, mod of E1 square I can write in terms of intensity, and if I replace this intensity with this our famous equation, then eventually we will have del E1 dz is I into k0 I1 E1. So, my equation become quite simplified, and this simplified thing should have some solution, and if I find this solution, it will be simply E1 z is equal to E1 0 e to the power of I into k0 I z. So, we have a modulation in phase. We will see that in the next class also, but here if I want to find out the total electric field E1 omega, which is half of E1 e to the power I k1 z minus omega t, then this E1, which is the amplitude of this quantity, can be now replaced by this solution. So, I write E1 0 and then the corresponding phase. So, that means amplitude of these things will not going to change, only the phase will going to evolve with z. Here you can see that when z equal to 0, E1 0 is E1 z is equal to E1 0. So, gradually the phase will going to evolve, and if I now write this total phase of the total field E1 z, then I find that these things is now changing. this total electric field, the phase term is changing, and in this phase we have a propagation constant. Now, my nonlinear propagation constant k prime is k1 plus into k0 I. So, n2 k0 I can be written in this, because k1 is simply omega by c into n0. So, omega by c is k0. So, k0 if I take common, so n0 plus n2 I multiplied by k0. So, this refractive index change multiplied by k0 is our new phase. So, this is our solution, this is our new phase. So, what I find that only the phase of these things will going to change. When I calculate the entire thing, we find that only the phase of electric field is going to change because of this Carr effect, which is called the cell phase modulation. So, today we will like to conclude our class. So, today we learn about the cell phase modulation, and for cell phase modulation we find that if a electric field is launched in a system which has a Carr nonlinearity, what happened that its phase will going to evolve, and because of the evolution of the phase, the propagation constant k is now changed. Previously it is k, right now it is k plus some term, and this extra term is coming because of this nonlinear refractive index change. So, with that note, let me conclude here. So, thank you for your attention. See you in the next class, and we will discuss the cell phase modulation again in the next class in detail. Thank you.